Hello, everyone. Welcome to this new Datadog On episode. Today, we are going to be focusing on the topic of caching. Datadog On is a series of events, live events, in which we invite engineers working every day on Datadog itself, not only engineers, but also product owners and designers, to discuss a particular technology or a problem that they want to solve, and how they're solving it at Datadog. So this episode is being recorded. Every other episode had been recorded before. So if you want to catch up with any previous episode or this one, once it's available in a couple of days, you can visit our website, which is datadogon.datadoghq.com. Some housekeeping items. We are going to leave about 10-15 minutes at the very end for questions. So should you have any questions, there is a Q&A button in your Zoom client, and you can basically leave the question there. You don't have to wait until the very end to ask your question. So as soon as you have a question about the content that you're seeing, feel free to leave it there, and we will go through the list of those questions at the very end. Okay, so without further ado, we can get started. Just some notes about Datadog itself. So Datadog, for those of you who don't know, is a monitoring and security platform that helps companies improve the observability and security of their infra and applications. Obviously, we use heavily Datadog internally as well. So we use Datadog to monitor Datadog. But this series is less about Datadog as a product, although obviously to solve some of the problems that we have, we need to use observability, and we use Datadog for it. But it's more about the internals, how we build Datadog internally. My name is Sara Pulido. I'm one of the co-organizers and co-hosts of Datadog On. So if you have any feedback about the series, or do you have any ideas on topics that you would like us to cover, feel free to reach out. I'm always happy to listen to any suggestions and feedback. But the important people today to talk about caching are Jess and Mitch. Jess, do you want to introduce yourself, please?
Thank you. Hi, everyone. I'm Jess. I've been a site reliability engineer and a software engineer in various infrastructure team and products for about 10 years. I've joined Datadog about a year and a half ago, originally as a senior software engineer, but I fairly quickly switched to being the engineering manager of the caching platform team about a year ago.
Nice, Mitch.
Great, thanks, Sarah. Hey, everyone, excited to be here. My name's Mitch. I am a EM at Datadog. I've been here for about 2 years. I joined as a staff engineer to kick off the caching team. Excited to talk about all our work here today. And now I manage a few abstracted storage services around caching, transactional storage, and search.
Great. Thanks a lot for joining this session and sharing your knowledge. So just before we get started, just something more about Datadog. It's the scale that we run on, because some of the decisions that we make, not every decision, but some of them are very related to the scale that we're running. So Datadog has more than 23,000 customers, and obviously we are a monitoring company, so we are gathering telemetry data from those customers. And if you add up all the hosts coming from those customers, that's millions of hosts that we gather telemetry from. And that adds up to trillions of data points per day that we need to ingest and process so our customers are able to make sense of all that data. So let's get started with the topic today, which is caching. And when I was preparing this topic, I wanted to start with this question, like, what's the deal with caching? Because it's in jokes about computer science. It's always mentioned as something that is very difficult to solve properly, but also very, very needed for teams. So Jess is going to start shedding some light on the topic. So Jess, if you want to go ahead.
Yeah, so like going back to basic of what is a cache. Basically, it is a hardware or software component that is used to store data for faster future requests. Like one of the characteristics of a cache is often the data can be stored elsewhere. It's just stored in a faster space than your source of truth, or it could be the result of an earlier computation, so you can reuse a value you've calculated multiple times without having to spend the resource to compute it again. It's pretty much everywhere in computer science. Some example of caching you've seen or encountered is, for example, in your browser cache. Every modern browser today will store a copy of websites you visit in your computer so that the next time you visit that website, they can load the page much, much faster. That's an example of software caching. One example of hardware caching is in your CPU. There is multiple layer of cache that are from faster and more expensive and smaller to still very fast, but a bit more cheaper, that will be a lot faster than your memory, your live memory, or your hard drive. And if we want to zoom even bigger, another example of caching that exists is content delivery network. As an example, if you're in Australia and you want to watch your cat video that was published in Europe, it's going to be very slow, it's going to be very hard to load, and it's going to be a much better user experience if you were to move that cat video and make a copy of that video in Australia. The type of caching we're going to talk a bit more in detail today is what we call distributed caching. The idea is when you run an application in the cloud, you may have a fleet of servers that is really your application layer, and you have a database or backend service that you use to serve your traffic. The problem is that that backend might be not fast enough for your use case, or it might be not able to handle the load or the query per second, your QPS, that your application is experiencing. And what you can do is to add one component in between both, which is your remote cache. Instead of having your cache being really part of your application server and do an in-memory cache, you can gain a couple of advantages by doing that. The first one is you can decouple the lifecycle of your cache from the lifecycle of your application servers. Because with an in-memory cache, if you turn down your server and bring it back up, it's going to be being brought back up empty, and you're going to end up hitting your backend right away. By having a remote cache, whenever you bring your server back on, it will be able to find information in that remote cache, and it won't create a spike of traffic on your backend. Another big advantage of using a remote cache is that if you have your application server A that receive a request from a user, do some calculation, and put that calculation in that remote cache, when a request comes to server application B that need to perform the same calculation, they can find that answer directly in the remote cache, and that will be able to serve the user request much faster. But with caching, there is a lot of risk, right? Like one very common joke in computer science is that there is two hard problems. The first one being naming, second one being cache invalidation, and the third one being off-by-one errors. And generally speaking, the main primary risk with caching is stale data, right? If you save a web page from a remote server on your local computer and you look at it again, there is no guarantee that that web page was not changed by the administrator. So whenever you build an application that is using caching, you need to think about, how can I serve this stale data? When do I need to invalidate that data? And when do I need to refresh my information and go back to the source of truth? And you have to really build your application with that delay in mind. Another risk related to caching is that eventually your cache might become load-bearing. You might be in a situation where you have a backend system that can handle, 1,000 requests per second. And then you add a cache in order to scale to bigger level, and now your application can serve 10,000 requests per second. What happens when your cache fails? What happens when your cache goes down? All of a sudden, the 10,000 QPS are going to go to your backend system, and you can enter this mode where you have a cascading failure, where your backend system falls over, and the solution to recover is to use your cache, but you can't put the data back to the cache because you can't read your backend. So whenever you start introducing caching to your application, you really need to think through those problems. And there is scenarios where using a cache is probably not necessary. If you are building an application where your backend system can handle the load and can handle like a speed at which you need it to perform, introducing a cache might be an unnecessary complexity versus just using your backend directly.
Good. Thanks a lot, Jess, for starting this conversation. And obviously, both of you are part of a team called Caching Team, but I know that team is fairly new. It's about 2 years old, but Datadog has been around for way more than that. So what, if you can, to explain a little bit why that Caching Team in the end was created, Mitch, maybe you can tell us a little bit of what Datadog was using before that Caching Team.
Yeah, absolutely, Ara. Thanks for the intro there. And, you know, to your point, caching has been about a 10-year journey at Datadog. We've needed caching about as long as we've been in production. So I'm going to try and give a little abridged version of this story. But in the story, I'm going to talk about some evolutions of caching at Datadog. And this has really just occurred as Datadog has scaled from a startup to the company it is now. You know, in terms of like number of products and the scale of our customer workloads, a few times we've need to go back to the drawing board and re-architect how we approach caching. So where did we start? Well, when Datadog was a startup, we ran in a single AWS region. So when apps in that region needed a cache, they reached to Elasticache. This is Amazon's managed service for basically running Redis. And really, it was really easy to use. It worked well. Some of the initial use cases included like the web front end would use it to cache things like auth session states, user properties, like imagine if a user favorites a dashboard or something. Here, the idea is just to speed up page load times, keep the Datadog app feeling snappy as it still is, and just scale with that load. That worked well. And then as other apps came along, well, this Elasticache infra was already set up. So they pretty much just used the same cache. And this was okay. You know, thankfully, they separated the key spaces so we could have this mixed multi-tenant workload in Elasticache. But some of these apps grew quite large and the cache started to grow very, very large with it. So some of the pros of this approach, one of my favorite things for the engineers that started this was that they created this pluggable cache interface. This interface turned out to be really future-proof, and we're still using it 10 years later. And this has allowed us to plug in different caching backends depending on the needs of the day. And also just being quick to get started, right? Elasticache is a nice managed service. People get caches running quickly. Some of the issues with this approach, I guess, is the first like isolation mistakes, I suppose, where we had a single large cache, and that meant that whenever there was an incident, there was a pretty large blast radius. Now, it's easy to say now that maybe we could have just run multiple Elasticaches, but that was the situation of the smaller company. Also, as Datadog has started moving to multiple cloud providers, there's been some nuances between the managed caching offerings of the different cloud providers, and that was a bit of a challenge. So as Datadog moved to a multi-cloud environment, expanded to GCP and Azure, we've actually made a successful bet on Kubernetes. We've started migrating our workloads to Kubernetes at this point in time, and that included our caches. So teams now could deploy their own Redis caches in Kubernetes. In this example at the top, we've got an app which there is a Helm chart that they could use. They sort of need to understand it, but it's self-managed. They can deploy their Helm chart and use it. So here we see an app that's connecting to a single Redis pod running in Kubernetes. That gives us like quite a bit of runway, to be honest. You know, we can be caching gigabytes of data, 1,000 requests per second. And, you know, if this was just for speeding up some of the page load times, like I was describing before, you know, this is great. This is fine. Then other apps came along that maybe needed a bit more data persistence, like in terms of the risks that Jess was talking about around a load-bearing cache. In this case, what we have is we're using another mode of Redis called high availability, where we have a primary and a replica. And the primary streams to the replica, and if the primary restarts or crashes, the replica assumes that role of primary, right? And what this means is if there's a more sensitive database or backend behind this cache, we can keep that load-bearing cache running in some of those maintenance events, I suppose. But finally, other apps came along and they had even higher throughput. And so for that, we use another mode called Redis cluster. Redis cluster was a different Helm configuration, and what this allows us to do is sort of horizontally scale, create more shards to our cache, and get more of that throughput that we needed for these bigger apps. Now, this was fairly tricky to run in Kubernetes, but it was a good move and helped us continue to scale. So some of the pros when we're looking at Redis on Kubernetes, number one for us, it was just cloud agnostic. So Datadog's Kubernetes sort of compute layer is the same everywhere. And so this was a big simplification for us as Datadog was running on many clouds. Also, through the Kubernetes abstractions, we got that isolation, right? So every team was running and managing their own cache. So the failure modes were looking much more favorable. And the flexibility, right? So we've got Redis, Redis HA, Redis cluster. There's also a configuration using Envoy, which I'll touch on soon. In terms of the cons, I guess, well, that flexibility is both a pro and a con. So we had some fragmented configurations. Some of these Helm charts were getting very confusing with lots of config options. I guess there was like knowledge silos, right? So different teams ran different configurations and it wasn't always clear who to ask for help with what thing. And just sort of a lack of ownership there. There was no documentation or limited documentation. And then with this just came lots of challenges of operations, of scaling based on efficiency and throughput. And really, this just became a burden for every engineering team. So caching was just running everywhere, and every engineering team was having to run these, was having to think about their Redises when they just wanted to focus on the product. And here on the right, this is an illustration, but this is a Datadog container map. And truly, this is what it looks like, where there were so many different cache deployments of different shapes and sizes. And when I saw this, I was thinking of Rey from Star Wars when she was saying that I didn't know there was this much Redis in the whole galaxy. So there was a lot we wanted to do here, and that's where we started.
Cool. And so I guess this is the time where enters the caching team to try to solve some of those issues.
Yeah, I guess so. That's right. And so the caching team started in 2021, started with, there was 2 of us and the team has grown. There's a photo of a recent fun event of the team and some of the friends of the team. And really we were just coming on board to try and own some of this infrastructure. We saw a lot of fragmentation. We saw a few painful incidents, a bit of a lack of ownership. And we really just wanted to see what we could do to improve this landscape. I think for Datadog, the company was at the right scale and caching was the right criticality, that it was time for an internal sort of platform team to own this stuff. And when we started our team, our mission was pretty straightforward. We just really wanted to make it easy for teams to add caching to their systems. And we want it to be simple, reliable, and scalable. And these are some of the themes that we'll be touching on in this talk. When we were looking at that landscape, as Ray was, we realized that lots of teams run Redis, and Redis is great. It's easy to use, it's efficient, it's simple. But as we were hearing, there was growing complexity in terms of the burden to understand these Helm charts. There were ops overheads. That could be deployments, it could be security requirements, it could be end-of-life version upgrades, and also just the scaling for a balance of performance and efficiency, and the reliability risks. So from those like scaling and isolation errors, we did see some large outages. They did trigger some of the cascading failure modes that Jess was describing, and we knew we had to do something different. So we as a team decided to build an internal managed caching service that we call Ephemera. This is what I was excited to introduce today, or we're excited to introduce. And Ephemera aims to be simple, reliable, scalable, and isolated. Reliable in terms of us having a team behind it, an on-call rotation, SLOs, scalable being horizontally scalable and sort of auto-scaling based on load, and isolated just to avoid those noisy neighbor issues that we've been talking about. Another thing for us that we really want to focus on being that sort of managed service is that great user experience. So making sure that it's easy for teams to turn up new caches, I'll chat more about that today, and being a drop-in replacement for existing caches using that nice interface we had. The other thing that was sort of subtle in our team mission is we really just wanted to focus on caching. So Redis as a piece of software is really powerful. It can do lots of things, but we wanted to solve the caching use case as best as we could, not be general Redis DBAs or something of the sort.
Great, thank you. Yeah, I like how you mentioned that it was that the point where it became painful for teams to become their own operations. It was the right time to start thinking about different ways to do this as a service, and we will touch on those points a little bit later in the talk. So I'm curious on how do you design a system like this? Because when I think about this, I think that from a technical point of view, is a little bit of a greenfield. Like you can do whatever you want from the very beginning, from scratch. But software system is not only the technology, it's also the culture. And from a cultural point of view, it feels like a brownfield. Like teams were already running Redis in production. They were already having those caches. So how do you approach a problem like that? Like you have something that is already being used successfully in many, many cases by the teams, but you want to do something that is better. So yes, can you give us some points on how did you approach this?
Yeah, absolutely. When the caching platform team started, really the first step was to do proper post-mortem analysis. Caching has been used at Datadog for many years. We've seen many incidents. We've seen many scenarios on how Redis could break in unexpected ways, especially running on top of Kubernetes. We've seen how much operation load was needed to do. And really what we looked for is what are the most common problems? What is the biggest chunk of teams and support that we can gather into one place to really help them and solve the most problem possible without going to try to solve every single problem. So really the first step was in the Ephemera feature was to define a very simple API. Get, set, delete, and the equivalent bulk operation, many get, many set, many delete. And it turned out that this very, very limited and simple API is enough to cover the wide majority of caching use case at Datadog. Actually, even the delete and many delete is only used about 5–10% of our users today, so it's almost a nice to have. One thing that's interesting to mention here, there is no scanning functionality. In the context of Datadog, cache is never used to, well, our cache is never used to scan anything. So that's a feature that we did not build and then made something a lot simpler for us to build infrastructure underneath that. The second big feature that's already mentioned by Mitch is single tenant. We want to make sure to maintain this isolation, making sure we can roll out caches and update progressively. We don't apply the change to everyone at the same time, and we can really reduce the impact of an incident when something bad happens. Another thing that been mentioned is auto-scaling, which I will let Mitch talk a bit more in detail in a few slides. And here we enter kind of like the more like, how do you decide to invalidate cache? The approach that we decided to take in Ephemera is enforcing TTL. Deciding that if you're writing a value in Ephemera, that value will be valid for the total duration of its TTL. And depending on the use case, depending on the team, sometimes that TTL can be 5 minutes, and some team have a 24-hour TTL. But because we are enforcing TTL to be there, we are enforcing team to approach using Ephemera as a cache, and they can mistake it as a persistent long-term storage system, which is very important because it's enabled us to be volatile. Basically, the idea behind Ephemera is that you can write into Ephemera, and most of the time you will be able to read that value that you wrote. But it is not a guarantee. With something like Redis HA, there is this guarantee that you always have a replica of the data, but this comes with quite a bit of a cost. You need to keep 2 copies of your data at all time. By being volatile and not having that strong guarantee that you'll be able to read back, we can keep only 1 copy of your data. And all of a sudden, the cost of running this infrastructure is much lower, and it gives us more freedom to build the architecture underneath as well. The next one is to be high availability. And here we're talking about access to the service and not necessarily getting the data. We're not always going to have your data back, but we will tell you about it. You will be able to rely on the cache to always be available in terms of access. And if we lose some piece of data, you will be able to rewrite it again, like much, much faster and much more easily. And the last thing is to be very low latency. Again, like by simplifying the guarantee that we have, by really focusing on the minimum set of requirements, we were able to build a system that's extremely performant across all of our operation of all our system, including bulk operation, or P50 latency is under 2 milliseconds, and our P99 is under 15 milliseconds. So the way we kind of like what scale can we reach with this, right? This is a fairly low set of guarantee. It's a very simple API. Is that really enough? And the answer for Datadog is yes. We have tens of millions of keys per second being requested across all of our caches. We have a very stable latency distribution, as you can see on this graph. We have dozens of teams inside Datadog using this system, which is supporting tens of products that all of our users use every day. And today we have hundreds of deployments of Ephemera. And again, thanks to that simplicity that we built into the system and the guarantee, turns out that we have a very quiet on-call rotation. The system has been built in a way that's very stable and enable us to focus on providing a better experience to user and providing better performance in general.
Great, thank you. Yes, it's actually super nice to see that latency distribution being so to the left and not having weird peaks elsewhere. So moving so what's the architecture of Ephemera? What that makes this possible? And Mitch is going to give us a little bit of overview, high-level overview of the architecture of Ephemera.
Yeah, absolutely. I'm excited to go a level deeper, so let's do it. Looking at the diagram on the screen, what we see here is the Ephemera architecture. It's pretty simple. Here in this green dotted box is what we call an Ephemera installation. This is a fully managed cache deployment, and we can deploy it in any of the Datadog regions. As Jess mentions, we really focus on keeping this as simple as we can, stateless, so making it easy to recover, and just generally focus on the failure domains, again, just to minimize those incidents. I want to sort of break this down a bit, and we're going to talk about it from the right to the left. So starting on the right, here we see a fleet of share nothing Redis pods. So these are pods in Kubernetes that are running the Redis binary. They store all our cache data, of course, in memory, but they don't have knowledge of each other. There's no replication, there's no gossip protocols, there's no control plane. They're all just an individual shards of our large caching fleet. As Jess said, Ephemera is volatile, so this works fine based on our requirements. We don't use Redis cluster, Redis HA, or any of the other fancy operators, and this is mainly due to a perception of operational overhead, cost, and just the reliability of these systems to bounce back in sort of disaster scenarios. There's no shared state, there's no control plane. Kubernetes can quickly reschedule any of these Redis pods as needed. In the middle, we have our Ephemera API server. This server routes cache requests from our client across the distributed fleet of Redis pods. You can also think of this, I guess, as a load balancer or a proxy or a front end, but basically it's a stateless microservice. We've written it in Go. It can auto scale to many pods. And as a matter of fact, it's been inspired by Envoy's Redis filter. So for those that don't know, Envoy is a distributed proxy that was originally built by Lyft, and it has some capabilities to route Redis requests. We actually used that at the very start of Ephemera. However, the core features that it provided weren't that advanced, and we decided to switch to our own Golang implementation. And this allowed us to use some Datadog specific features and build some extensions that we're going to touch on in this talk. Between the API server and the client, one notable difference between our API server and Envoy is that we actually use gRPC. So gRPC is really nice for us because it gives us some standard authentication, service discovery, and observability in our Datadog production environment. I want to say that, like, in general, I think Datadog's really happy with gRPC. We did a similar Datadog On talk of just gRPC, and I'd encourage you to check that out if you'd like to learn more. And then on the far left side, we have our Ephemera client. This is basically a thin wrapper of the gRPC client. Why this is important for us is because it implements that standard cache interface that I've been talking about. With this, existing workloads in this brownfield production scenario can switch to Ephemera in just a few lines of code. So stepping back, looking end to end, our architecture, I think I'm pretty proud, is simple and fault tolerant. I think one of the most interesting parts of it is how we route requests. That's that purple box in the middle of the API server. We call it our sharded Redis library, and I wanted to chat a bit more about that. So that sharded Redis library uses consistent hashing. Consistent hashing, if you haven't heard of it, is basically an algorithm to shard a workload across multiple backends. Some of the features of consistent hashing, I guess, is that it distributes the key space balanced across the backends, and it does that using no control plane state. So if you imagine something like range-based sharding, usually that would require a routing table or something of the sort. But here with consistent hashing, it's all a bit of mathematics to decide. Some of the properties of a favorable consistent hashing algorithm, in addition, is that there's minimal key moves when you scale. So looking at this diagram on the right, if we were to add a fourth Redis pod, it wouldn't cause all the keys to churn and reshuffle, and instead there'd be a minimal set that would move to that new Redis pod. Similarly, when we talk about key churn, another favorable property is a stable assignment during restart. So if one of these Redises shuts down for any kind of maintenance event and comes back up, it's reassign the exact same key set. It doesn't cause another big reshuffle event. Specifically, in Ephemera, we use the fast maglev algorithm. I have cited the paper down below, but one of the nice things about it is it has constant time key routing. So if we look on the next slide, what we see is that we have a cache key, in this example, Bob, and that gets hashed to a certain virtual bucket in the API server. And then based on the lookup table, we know to immediately route that to the Redis 2 endpoint. So this works really well for us. It's implemented in our Golang API server. And yeah, that's what I wanted to share there. Thanks.
Good. Thanks, Mitch. If anybody has questions that they want to dive deeper in the maglev algorithm, just use the Q&A button and ask as many questions. Mitch knows it all. So the next thing I want to start discussing is some of the improvements that we've done on top of that simple architecture. And one of them is how you've been improving data persisting. And it seems like a little bit counterintuitive because yes, you've been mentioning from the beginning and repeating it over and over again. And I guess you repeat it to your customers, your internal customers as well. Your data is volatile, but yet you've done some improvements to improve data persistence. Why is that? And what strategies are you following for that?
Yeah, of course. At the end of the day, our objective is to provide as much value to Datadog as possible, right? We could, in theory, accept every write and not write anyway and always fail on the lookup, and we will match our contract. But at the end of the day, every cache miss can mean a web page takes longer to load, a metrics query takes longer to execute. So there is some real user impact to those cache miss. So our objective, if we're not going to eliminate every cache miss, is to still limit them as much as possible so we can make the most useful service as we can. So as an example of what has been happening in the past, when we used to update already sets, right? We maybe here an example, there is a Ephemera cache with 3 Redis backend. Whenever we need to make an update to Redis, is there increase the version or making some Helm chart changes? First, we had to take the Redis pod, shut it down, or maglev algorithm will rebalance the keys, wait a few minutes to make sure that we are not too aggressive in wiping the data, and then bring it back. But when it comes back, it's Redis, it's in memory, the data is gone. So which means that over a certain amount of time, when we do an update, your entire cache is going to be wiped over time. And this also means that because we don't want to be too aggressive in that data deletion, we wait 5 minutes between each updates. For a small cache of 3 Redis server, it's fine. For a very large cache with maybe 150 Redis server, that means that this update takes a very long time, and there is quite a bit of thought around the operational of those things. So what we came up with is something we call the update helper. The idea of the update helper is to have this side Redis pod that is running next to your regular Ephemera cache. And now we have a 6-step process to do an update. The first step is to simply shipping all the data of the Redis pod you want to shut down. So in this case, Redis 2. We shove all this data to the side Redis pod. We update the API server for this side Redis pod to assume the identity of Redis 2. And now all the traffic from maglev is being redirected to that side Redis pod. Now we can safely shut down the Redis 2. We bring it back up, and then we do the same process in the other direction. We ship all the data back from that side Redis pod to Redis 2, and Redis 2 reassume its identity. And by doing this, we can basically do a graceful shutdown of a Redis pod without any data loss. And that enables us to also update our Redis pod much faster, because shipping the data back and forth actually takes anywhere between 5 and 30 seconds, and then we can update and move on to the next pod. So all of a sudden, our 150 Redis deployment takes 6 times less time to be executed.
Nice. Yes, thank you. Another improvements that you've been adding to the system is related to networking, because obviously you mentioned that this is a distributed cache. And for any distributed system out there, you need to take networking very, very much into account. So I know that you had some issues. So what was that?
So one of the first things we started doing with Ephemera when it started is we addressed the smaller size use cases. And at the time, we were using a certain Go library to talk to Redis, which was using reusing connection, but only enable us to send one request at a time on a given connection. So we'd have a connection pool, we grab a connection, we send a request, and we have to wait for the response in order to be able to reuse that connection for a second request. The problem with this approach is whenever a request timeouts, we have to close that connection. There is no way to know if you reuse that connection if the response you get is from your new request or is from your previous request that actually timed out. And opening connection and closing connection is not cheap. There is a lot of system call that are involved in this. And we realized when we started addressing larger scale use case that we could enter this spiral down of death where Redis would be slightly stressed. Some requests were starting to time out, meaning we had to close those connection and open new connection, which is CPU intensive, which meant that Redis got more CPU store, which meant that more requests was timing out. And even once the spike of traffic or the request that caused the event to start was subsiding, Redis was staying in this bad state where we kept opening and closing connections. So the way we solved this problem, and we try to reach that new level of scale with Ephemera, is switching to a Go Redis client library called Redis, and it's implement pipelining. The idea behind pipelining is that you can send multiple requests in parallel on one connection by tagging each of those requests. And then Redis knows how to tag those response in a similar way, meaning that now if you're timing out on one request, if that response arrive is still sent back later on, you can safely ignore it knowing that it was a previous request. This meant that whenever we had a request timing out, we no longer enter that spiral of death, which meant we were able to recover more gracefully and use auto-scaling to handle the new level of spike. And one of the really cool things about this change that we really was working for one specific use case is that this change ended up improving the entire fleet of Ephemera cache. As you can see on this graph, the bottom line is showing basically us updating our server to the new version. And once we've updated the majority of our server, you can see at the top the reduction of how much CPU or Redis deployment actually use. The dotted line being the week before when we did not have that improvement rolled out everywhere. And the bottom line, which is about 20% lower, is showing this improvement. And I think this is really a really good example of having one dedicated team dealing with caching is very useful, because one team might have had this problem, but if they were only managing their own cache, the rest of that data would have not benefited from that improvement in the same way.
Good, good to see, which brings us to to what you were mentioning, internal managed services. So Mitch, when is the right time and how you do it?
Yeah, that's a great question, and I'm hoping to take away of this talk. And I just wanted to discuss like how we approach running Ephemera as that internal managed service. I think some of these considerations in many ways are similar to any startup running a platform as a service. We really focus on our customers. We care about isolation and scale, as we keep saying. I think, to be fair, internally, some things are easier for us. We have to deal less with like abuse or billing our customers. But yeah, I just wanted to share what I think we found most important. And this I also want to stress is around managed service. It's not necessarily about dedicated teams. I think you can start with the APIs, thinking about the primitives of the service, and then a dedicated team may only be needed once you reach that large company scale. So I wanted to throw us back to the slide that Jess had on the scale of Ephemera and highlight these two boxes, right? So for us, we're working with dozens of different teams, excuse me, and we have hundreds of deployments. When we were starting, we just had early adopters. We deeply understood their use cases end to end and talked a lot with them. But now with hundreds of deployments, right, we just can't understand every use case. We do keep our APIs really simple, but teams have still found creative ways to use Ephemera. So it's been a matter of us putting in some guidelines and some frameworks to help us scale to this size. And I really wanted to sort of break that down into these 4 managed service tenants. I'm going to talk more about each of these, but I wanted to touch on self-service, data ownership, auto-scaling, and isolation. And in general, I just think these are some of the important principles to help scale to hundreds of deployments. Starting with the first one, self-service. Here, our objective is that Datadog being a distributed company, a global company, we wanted that teams in Europe could modify their Ephemera caches, deploy a new cache, while we, the caching team, primarily in New York, are blissfully asleep. So we do that using self-service workflows. We've created workflows for a number of common user journeys. I think the primary one is deploying a new cluster, but some of the other workflows or user journeys include like deleting a cluster, changing cluster authentication, and so forth. To do that, we use Temporal. It's a great open source workflow orchestration software, and then users interact with these workflows through a combination of a CLI and some GitHub and Slack ops. So we see on that screenshot on the right, as an example, I created a new cache for this talk. We can see that the Temporal worker sent me a GitHub PR to review. This included some of like the Helm chart changes and so forth. And then once I push the approve button, Temporal shepherds through that PR through CI, merges it, and then starts the deployment process using our internal tools. And then once the cache is deployed and ready to use, our self-service automation sends me a DM on Slack, says it's ready to go, and gives me some tips for getting started. So nice user experience. The second tenet I wanted to touch on is data ownership. So one of the important things we gather when people create new caches is some metadata about the cache. So this is, for example, the team, their use case, and so forth. Part of this metadata includes also the services that are intended to access this cache, and then we have authenticated access to these caches. I think even if you ignore bad actors, having authenticated access is really important just to limit the access to the intended users. It's possible someone might have copied some code or didn't realize there was some library that was using a cache. And by having that access enforced, then we can really know who's using what. Also, in a large Kubernetes context, sometimes there can be some service discovery, service identity bugs, and that authentication just makes sure that we know that clients are talking to the services they intend. Finally, with this data ownership metadata, we just get clear escalation paths and contact details for all of our users. So on the right here, we have an illustration of the Datadog service catalog, but we really use this internally. For every cache that we operate, there's an entry in the service catalog, which includes the team that owns it, who's on call for it currently, Slack contact details, and so forth. And this is just really important that if something goes wrong, we know who to reach out to, and it can help us reduce the resolution times for an incident. Third thing to touch on is auto-scaling. So we, as the caching team, just can't hand tune hundreds of deployments, right? So we've mentioned that Ephemera horizontally scales. We use auto-scaling, and Datadog has an open source Kubernetes controller called the Watermark Pod Autoscaler, and we use that internally just to keep our caches at the right size. In the screenshot on the right, I've chosen a particularly chatty cache, but here we see over a period of a week, a cache's Redis deployment scaling between 7 and 14 pods based on the CPU watermarks that we set. And we set them doing some benchmarking. The last thing to touch on auto scaling is just bin packing, right? So this is a concept in Kubernetes where we have some large Kubernetes nodes, and then we bin pack smaller cache pods on those nodes. And where this is really helpful for us is that if a team wants to create a new small cache, the marginal cost of bin packing in that new cache is basically zero. So whenever someone comes to us in the team is like, oh, I'm not sure if I should use a cache or not, generally the answer is just go for it, because at this scale, it becomes really economical for us. Last thing to say is isolation. So going all the way back to when we're talking about that large multi-tenant cache, we did see some big blast radiuses when things went wrong. But thankfully, fingers crossed, since we've deployed Ephemera, any incident we've had has been pretty limited in scope. And how we've done this is, of course, what we keep mentioning, which is just isolated deployments per use case. But then also in our API server, we use a combination of load shedding and circuit breaking. If the server's overloaded or if there's some query of death, we can stop the bleeding quickly and avoid it turning into a cascading failure. The other thing when we talk about isolation, more on like a human error and software bug point of view, is it's really important to have gradual automated deployments. So on the right here, we have an illustration of our actual deployment plan, where in Ephemera, we go region by region and deploy our caches slowly. We've sort of made 3 classes of caches. First of all, we deploy our canary caches, which is, the canary in the coal mine. These are our internal caches that we can use to validate through synthetic testing that everything's working as expected. Once that's deployed, we wait 15 minutes and use a Datadog monitors to check that it's all looking good. And then if that does pass, we progress to rolling out our standard class of caches, which is the majority of our users. Once that's done, another monitor, another 15 minutes, and then finally we deploy a critical class of caches, which, maybe that's a little unfair, but these are the use cases we really, really care, and the business cares about their uptime. So then after that's done, another 15 minutes and progress to the next region. Final thing to touch on here, and I know this is a lot, but is isolation from like a developer experience point of view. I think it's really important for our users and also the Ephemera developments that it's easy to experiment. So we have a robust experiment framework, and we also have developer environments using Tilt, another open source tool, so people can get up and running with an experimental cache, try some A/B testing, play with it without the need to experiment in production.
Fantastic. Thanks, because I think these tenets, as you mentioned, can be applied to other managed services that may or may not be related to cache. Good. So what's next, Jess? What's in the roadmap for your team?
We have a lot of things like planned for the future. Like one of the first things we're starting to think more seriously about is chaos engineering, right? Ephemera is a volatile cache, and even though we're trying to make data persistence something much more common, we're still going to be a volatile cache, and there's still scenario that we're not going to be able to guarantee that the data is here. So we want to make sure that if those events are rare enough that our user might mistake us for a persistent storage, we're introducing a little bit of chaos so they don't get too used to getting the data and mistake us for a database. Something else we want to work on is something we call multi-level caching. One very common use case we've seen at Datadog is user having an in-memory cache in their servers and using that as their primary caching service. However, whenever they restart and their cache is empty, they are using Ephemera to rehydrate their in-memory cache. I think we can do a lot as a team to just provide this as a wall, as a single box. They just have an Ephemera client, and there is in-memory caching just integrated in there, and they have to think about less things. And our North Star really for like the future of caching at Datadog is what we call transparent caching. The idea here is to have a user and team not even have to think about caching anymore. They could say like, oh, I want a Cassandra backend, and I can handle a 30 minutes eventual consistency. and then they will get a Cassandra client that has integrated caching with Ephemera that will be able to enable them to scale much faster and larger, and having much faster response time than what Cassandra could do in and of itself.
Good. Seems like there is still lots to do which is great to see, because it seems like it's a very simple service and you try to keep it simple, but at the same time adding features in a transparent way that doesn't change that simplicity, but makes things a lot easier for your users. Okay, so we are about to go for Q&A. We already have some questions popping up, so thanks for that. Before we go to Q&A, I would like to ask Mitch and Jess for one key takeaway, one thing that they learned about building these internal managed teams. So Mitch, do you want to start?
Oh, yeah, sure. Thanks, Ara. I think I'd probably just like to double down on what you were saying there around simplicity. When I was preparing some of those slides on the history of caching, it just made me realize that as we've gone through these evolutions, it has always been focused on simplicity and having the most simple solution for the scale that we're at. So we've only added complexity to Ephemera and caching in general when there was a specific need and a specific problem we're solving. But starting simple gives you that flexibility to iterate as you grow.
Good. Jess?
I think my biggest takeaway after what Mitch just said is around kind of like managed teams and managed service and platforms. It doesn't make sense for a small company to have a team dedicated to infrastructure, but you can really prepare the growth of your company if you take a second to think about your API. If you kind of like creating the simple API to start with to interact with your backend system, you can really standardize this user across your company. And as you grow and as you eventually reach a scale like Datadog is, where having this internal team is useful, you're gonna make your life a lot easier if there is already some standardization that team can build upon and provide a lot of value very quickly.
Good. And we have a question actually kind of related to that that we can reiterate during the Q&A. So thanks. We are going to go to Q&A, but if you think these problems are very interesting to solve, Datadog is hiring. So if you go to our career space, datadoghq.com/careers, please have a look to our engineering openings there because we are hiring across the board. I'll start with one of the questions. So there is a question related actually to consistent hashing. What is the difference trade-off between maglev and murmur, or why did you choose it? So maybe Mitch, you can answer that one.
Yeah, excuse me. Thanks for the technical question. What I would say is that maglev is more an algorithm for how the hash key space is mapped to the backends, and it actually doesn't prescribe what hash you use. So as a matter of fact, in Ephemera, we do use the murmur2 hash for going from a key to a 64-bit hash space. But then where maglev works, and that's in contrast to some other algorithms like Katama and rendezvous hashing, is how you go from that hash to a backend.
Very good, very good answers. Thank you. So next one. So this one maybe for Jess. How does Datadog tune the caching services based on the workload, read heavy versus write heavy? For example, one cache service that can be tuned for different workloads, or different caching service for different workloads?
I think really the key for us here is to not really care about the shape of the workload, is more care about what resources they're using. Right, like a write-heavy workload might be more CPU consuming, or et cetera, And by using the autoscaler that Datadog has provided, we can really just watch how much resources is actually used by this workload, and automatically either increasing the number of Redis servers that we're running or increasing the number of API server. And we can do all of this seamlessly and not really have to pay that close attention to what the actual work being done by the workload is. Okay. That's really something that's helped us being able to scale and support more team without having to learn what everyone is exactly doing.
And just tying it back to like concrete workloads, like we definitely have workloads on both sides of the spectrum, right? Like we've got the classic read heavy of you've got a database that's being accessed from many places and a cache helps there, but also on some hot write paths, like when we think of things like metrics, some of the pipelines end up having a lot of duplicated data, and we have some very large caches that dedupe some of that data to then minimize the write throughput on the downstream service.
Good. Another question. How does other teams, and this is we've touched upon during the talk, but just to clarify, how does other teams migrate from those team managed ready spots to Ephemera?
Yeah, I can start on that one. So certainly on the code point of view, the interfaces make that really easy. So there's not like you're rewriting the entire app. It's quite easy to switch over. But if we think about the production context, like we're running services 24/7, the key there is just dual writing. So as Jess was mentioning, a very convenient property of having TTL data is that if you were to dual write to 2 caches for up to the maximum TTL, then in theory, they should be identical. So we had a framework for pointing a sort of a wrapper that would point a cache to the 2 backends, and then we can slowly turn up the knob to make sure everything's working safely and migrate from the old cache to the new cache. 0 downtime. As a matter of fact, that's all in our libraries, so our users didn't really need to do much.
Yes, and that goes back to what you're saying, Mitch, that interface that was written like 10 years ago is still being used. Okay, so one question more about, I think it's more about how cache work in general. So one attendee is asking, how does users get that data from their source of truth into the cache? Is it something that Ephemera provides, or is more on the app code?
Like as of today, it's very much more on the app code. It's on the user to do that work. And I think this is really something that's what I was talking, right? At Ephemera in the future, and one of our gold star is to be able to offload that work from team. It's really something I think we can build. That's something we can bring a lot of value to the company at Datadog. But as of today, team have to manage their own interaction between their backend system and Ephemera.
Good. And there is a question, but I think that somebody was asking how do we perform updates on the ready spots without losing all data. So this has been covered on the slides. So don't worry, because again, this is being recorded. So in probably by the beginning of next week, if you go to datadogon.datadoghq.com, you will be able to see the recording and see that part, which was very, very well explained. One last question before we wrap up. So how do you observe cache performance? And this is very intertwined between what we do at Datadog, I guess. So who wants to take that one?
Yes, sure, I'll start. There is actually a Redis integration from Datadog that we use to like extract a lot of information from our Redis server directly. And then it's very much leveraging all of Datadog products through both metrics, logs, APM. And we try to very much use as much as possible the observability Datadog offer in order to get as much information as we can and understanding what is going on in our systems.
Sounds good. Okay, so we don't have any other questions from the audience, and actually we're in the top of the hour, so I think we can wrap up now. So thanks a lot, everyone, for attending and for the questions. It's always great to see people asking questions at these events. This is one of the main reasons why we do this. And thanks, obviously, Jess and Mitch, for joining us today. And again, this will be up, the recording in few days. So if you miss part of it, or if you want to share it with any of your colleagues, go to our website and you will be able to see the recording and share it with colleagues, etc. So thanks again, and see you on the next one.
See you all. Thank you.
Everyone, thank you.